Hello everyone. This is Ala Abu Hilwa, and today I'm doing my lab 3 physics. So an introduction to this lab is the purpose is to determining the mass of a black hole involving analyzing the orbit of a nearby star. This information can then be utilized to calculate the initial velocity required for a spacecraft departing from the planet's surface to orbit the black hole safely, avoiding collisions with both the planet and the black hole. The system in this experiment is the spaceship, surroundings is the black hole. Some of the fundamentals that we use are Newton's second law and the universal law of gravitation. We have two parts to this experiment. The first part is determining the mass of a specific black hole, employing computational models to simulate the curved trajectory of a star orbiting around it. And then the second part is determining the initial velocity required for a spaceship to approach very close to a black hole vicinity, but still manage to escape without collision. This is completely just coding. There's no physical experiment. So main formulas and ideas, we use Newton's second law, velocity update, position update, parallel and perpendicular components, and then gravitational force. These are very and highly important throughout this experiment. Okay, so we start with part 1. First of all, we initialize the conditions. So the mass of the star, 2 to the power of e to the power of 30, and then gravitational constant, 6.7 times e to the power of minus 11, and then time interval, 86,400, and then the default time is 0. We applied Newton's second law. Here we replace Fnet to dPdt, and then the parallel component, we code that, and then the perpendicular component as well. And then we find the mass using both the Fnet, the start position, the magnitude, and G. And this results in this. So we got the mass as 1.12 times e to the power of 34. The magnitude of Fnet is 8.3 times e to the power of 28 newtons. Fnet perpendicular parallel was 1.05 times e to the power of 28, and then perpendicular Fnet was 8.26 times e to the power of 28. Next slide. Okay. An explanation for this is in the context of space, the sole forces influencing the star are the gravitational pull of the black hole. Similarly, the spaceship experiences gravitational forces from both the black and the planet. Therefore, the net force is equal to the gravitational force, denoted as Fgrav. Since the universal gravitational varies, we replace average velocity with final velocity in our computations. If the net force component parallel to motion aligns with the direction of motion, the object accelerates. Altering the perpendicular net force component alters the object's direction. And then in part 2, which is don't crash, the system is spaceship surrounding planet or black hole. And we have the initial velocity that we use from guess and check, and then t equals 3,600. The initial conditions, we place first the mass of the black hole from the previous part. Then we place R, we calculate all of these, we place R hat, and then we find the force of gravity using universal gravitation, and then the distance from the ship to black hole. We place all these in the code. And then Newton's second law, we place both the update and the velocity and position update formulas into the code. And then we result in this. I'm going to speed it up just due to time because this video is very, very long. And then we result in the closest distance, which is 1.6 times e to the power of 10. Possible errors would be in part 1, running the program for longer to have a more accurate mass. And then for part 2, incorrect initial velocity due to guess and check method, and as well as time interval could be too short. And then finally, we ask questions: what initial velocity is required for your spaceship to enter a stable orbit around the black hole without colliding with either the black hole or the planet? For orbiting, the spaceship's velocity should align closely with that of the planet, with a slightly larger y component and a smaller negative x component to prevent collisions, so a similar velocity to this. And then the planet's orbital velocity. And then how are the net forces and its parallel perpendicular components different from the rate of change of momentum in parallel perpendicular components? So it represents the net parallel force to the direction of motion and calculate as the rate of change. It denotes the net force perpendicular, and then rate of change of momentum is expressed as final minus initial, and the momentum is mass times velocity. And finding the change is comparatively simpler than determining the net force.